High-performance computing centers are currently solving some of the most complex mathematical problems in mankind, covering areas like physics, healthcare, biology, among others. Additionally, these infrastructures are also thought to support big data applications. Since these workloads significantly differ from those of traditional parallel computing tasks, new challenges are arising. The BigHPC ambition is to simplify the management of HPC infrastructures, supporting big data and parallel computing applications. The proposed solution intends to develop a novel framework to efficiently manage parallel and big data workloads by combining new monitoring, virtualization, and software-defined storage components. The current work being made on a monitoring component has targeted the development of the monitoring probe actor. The monitoring probe runs inside a container which is deployed in the compute nodes. The monitoring probe is able to collect a range of different metrics from diverse resources such as CPU, GPU, memory, cluster parallel file system, network, disk, and processes. Running the monitoring probe in a container allows for the development of the container in a controlled environment and straightforward deployment in the compute nodes. In addition, the container is an isolated application from the main host environment. Therefore, it does not require the re-implementation or redesign of current HPC cluster software, providing the added benefit of being easily adaptable to run in other HPC centers. As a result of the versatility of using the monitoring container, it is possible that the container could be deployed attached to the running job. The virtualization manager uses two components to run user workloads in an optimal manner. The first component, labeled the scheduler, will combine input from the monitoring probe and storage manager with user workload specifications in order to place workloads on the cluster compute nodes such that they minimally infer and obey quality of service requirements. The second component, the repository, will maintain container image and software that are optimized for the clusters on which big HPC workloads run. The two components act in concert to run user workloads with optimal software and hardware support. BigHPC has developed a prototype of both the scheduler and repository, capable of curating optimal container images and executing them on tax HPC clusters through a command line interface. Specifically, BigHPC allocations can be created on HPC clusters, test workloads run on those allocations, and container image optimized for specific HPC clusters are uploaded and downloaded from the repository. Detailed studies were performed and published to develop best practices for optimal container performance. The prototype testbed consists of the BigHPC virtual machine for hosting the scheduler and repository and the Frontera HPC cluster on which test workloads are run. The next steps are to incorporate input from the monitoring probe and storage manager using the APIs BigHPC has developed, support the myriad workload specifications users may make, and combine those input and specifications to optimally place workloads on the HPC cluster. BigHPC aims at improving the storage performance for big data applications deployed at HPC infrastructures by following the software-defined storage design. This design considers a data plane component that implements different storage optimizations such as I/O scheduling and caching. Each optimization is provided as an independent data plane stage that mediates I/O requests between applications and HPC storage resources. To ensure that I/O optimizations implemented at this stage have fair access to shared storage resources, a control plane component with global visibility of the HPC infrastructure is responsible for coordinating and fine-tuning all stages. This poster presents our current work for the data plane component, namely, we have developed PIO, a framework that can be used to implement custom-made data plane stages that can be reused for different big data applications. We showcase this feature by implementing an I/O scheduling stage for the ROCS database, key value store, that improves the tail latency of storage requests. Furthermore, through PIO, we implement another data plane stage for ensuring different levels of quality of service for TensorFlow instances accessing shared storage resources when training a deep learning model. Until now, the BigHPC project has resulted in 3 prototypes corresponding to each activity: Actor, an high-performance container monitoring probe to collect containering metrics on compute nodes; the virtualization manager composed of the scheduler and repository; and Pio, a user-level library that allows system designers to build custom software-defined storage data planes. All the information regarding the BigHPC project is available at bighpc.wavecom.pt, and you can follow us on Twitter and LinkedIn. BigHPC is a UT Austin, Portugal 2019 strategic research project. It started on the 31st of March of 2020 with a duration of 36 months. The consortium is composed of Wavecom, Inestech, LEAP, UT Austin, TAC, and MAC. Funding sources are $799,000 from UT Austin, $748,000 from Portugal 2020, $233,000 from FCT, and also $202,000 of business self-funding.